Powering the future. What is a microgrid? Imagine a small, self-sufficient city powered entirely by its own energy sources. This is the basic idea behind a microgrid. It's like a mini power grid that can operate independently or in sync with the main grid. Microgrids are becoming increasingly important as we move towards a future of cleaner and more reliable energy. These localized grids are designed to provide power to a specific area like a college campus, a hospital, or even a small town. This means they can keep the lights on even when the main grid goes down. Think of it like having a backup generator for your entire community. Microgrids are not just about keeping the lights on. They're about creating a smarter, more sustainable energy future. By integrating renewable energy sources like solar and wind, microgrids can help us reduce our reliance on fossil fuels. This shift towards localized energy production is a crucial step in combating climate change. The engine room key parts of a microgrid. To understand how a microgrid works, we need to take a look under the hood. A microgrid is made up of several key components that work together seamlessly. Let's break down these essential parts. First, we have the distributed energy resources, or DERs. These are the powerhouses generating electricity from various sources. DERs include solar panels, wind turbines, and natural gas generators. Next is the control system, the brains of the operation. It manages energy flow, ensuring electricity goes where needed. Like a conductor, it ensures harmony. Finally, we have the loads, the energy consumers. These include homes and businesses and streetlights. The control system ensures a reliable power supply. Two modes of power-connected and independent microgrids. Microgrids are versatile systems that can operate in two primary modes, grid-connected and islanded. Understanding these modes is crucial to grasping the full potential of microgrid technology. In grid-connected mode, the microgrid is connected to the main power grid, drawing electricity from it when needed. This connection allows the microgrid to supplement its own generation with power from the main grid, ensuring a consistent energy supply. However, the real magic happens in islanded mode. In this mode, the microgrid disconnects from the main grid, becoming an island of power. This is particularly useful during power outages or emergencies when the main grid is down. Think of it like a ship that can sail on the open ocean or dock at a port when necessary. The ability to switch between these modes seamlessly is what makes microgrids such a game changer in the world of energy. Section 4. How microgrids work from grid to island mode. Let's delve a bit deeper into how microgrids transition between grid-connected and islanded modes. This process is orchestrated by the microgrid's control system, which constantly monitors the health of both the microgrid and the main power grid. In normal operation, the microgrid hums along in grid-connected mode, drawing power from the main grid as needed. However, if the control system detects a disturbance or fault on the main grid, it triggers a swift and seamless transition to island mode. This transition usually happens in a matter of milliseconds, so fast that most people connected to the microgrid wouldn't even notice a blip in their power supply. Once in island mode, the microgrid's DERs take over, providing power to the local community. When the main grid stabilizes, the control system initiates a smooth reconnection process, synchronizing the microgrid's frequency and voltage with the main grid before bringing it back online. This seamless transition between modes ensures a reliable and resilient power supply no matter the circumstances. Section 5. The upsides benefits of using microgrids. The versatility and resilience of microgrids come with a host of benefits, making them an increasingly attractive solution for a wide range of applications. Let's explore some of the key advantages of embracing microgrid technology. First and foremost, microgrids enhance energy reliability. By providing a localized source of power, they act as a safety net during outages on the main grid. This is particularly crucial for critical facilities like hospitals, where a power outage can have life or death consequences. Furthermore, microgrids can lead to cost savings on energy bills. By generating their own power, microgrid users can reduce their reliance on the main grid and potentially avoid price fluctuations in the energy market. This is especially beneficial in areas with high energy costs. Moreover, microgrids can help reduce our carbon footprint. By integrating renewable energy sources like solar and wind, microgrids can significantly decrease greenhouse gas emissions compared to traditional power plants. This shift towards cleaner energy is essential in combating climate change. Section 6. The downsides, challenges facing microgrids. While microgrids hold promise, challenges remain before they become mainstream. One major challenge is the high initial cost of installation. Significant upfront investment can be a barrier. As technology advances, costs are expected to decrease. Another challenge is the technical complexity of microgrids. Specialized knowledge is required for efficient operation. Interoperability issues also pose a challenge. Different microgrids use varying protocols and systems. Industry standards and collaborations aim to solve these issues.